So let me start by saying hello to everybody, and just to say that it's a great pleasure to be here in person at the ERI conference after 3 long years. Phoebe explained, and Christian also explained very well what was going on during these years. But this morning I have the honor of introducing Professor Lars Peter Hansen, whose work in economics over more than 40 years has left a huge footprint on the field. During most of his time, he has been on the faculty of the University of Chicago in a variety of capacities. Very early in his career, Professor Hansen won the prestigious Frisch Prize, along with Kenneth Singleton, for their article in Econometrica, Generalized Instrumental Variables Estimation of Nonlinear Rational Expectation Models. Since then, his work has been recognized by many awards, most notably the Nobel Prize in 2013, along with Eugene Fama and Robert Shiller for their empirical analysis of asset prices. Professor Hansen is widely known as the developer of the econometric technique Generalized Method of Moments, GMM, a method which has been widely adopted in economics and other fields and applications, who are fully specifying and solving a model of complex economic environment is awkward or inapplicable. Professor Hansen has authored or co-authored numerous books and articles in all top journals on a wide variety of topics and different aspects of economics. In short, his achievements are far too numerous to list here, especially since we don't have much time. But out of all these contributions to economics, the one that we will hear about today relates to uncertainty. His research has shown that when there is aversion to ambiguity and model misspecification, the development of robust control methods in the context of max-min expected utility can produce robust regulation. Climate change is an area of this kind of deep uncertainty, and thus it is an area in which Professor Hansen's contribution can help in the design of efficient climate policies. Professor Hansen, the floor is yours.
So thank you very much for those kind words. I appreciate the opportunity to share some ideas with you today. I come from a background of macroeconomics, finance, and econometrics, and I've been interested in climate issues over the last several years because there are obvious connections to things like the macroeconomy, and uncertainty, in my view, is central to thinking about such problems. So the title of today's talk is How Should Climate Change Uncertainty Impact Social Valuation and Policy? I have some collaborators, Mike Barnett, who's assistant professor at ASU, and Buzz Brock, who's a distinguished economist at University of Wisconsin. So what's the challenge that I want to focus on today? There's limits to our understanding of potential economic impact of climate change. Yes, we have lots of evidence of a human input on the environment. How that's going to play out over the future, though, is where the uncertainty comes into play. Today I'll be focusing on 2 sources of uncertainty and their interactions. One is, of course, the CO2 emissions today, the impact future climate. The other one is that climate change in the future then alters economic opportunities and social well-being. In both cases, uncertainties are central. And thinking about uncertainty in systematic ways using so-called decision theory leads to uncertainty trade-offs that I think are very important for when we think about policy in this arena and others. When we use models, we can build dynamic models that give us best guesses. Those models can also be used to figure out potentially bad outcomes. Part of the policy challenge is how do we trade off these best guesses from potentially bad policy outcomes. The other one is in a world of uncertainty, at some point in time in the future, we're going to know more. That puts on the table, do we act now, or do we wait until we learn more? In the case of climate change, at the same time we're learning more, it may be very, very costly to, at that point in time, do the appropriate mitigation, adaptation, or the like. So both of these, I think, are very important trade-offs. Both of these, uncertainty plays a central role. So the type of research that I've been doing with a variety of collaborators, we want to build computationally tractable methods for exploring subjective uncertainty. And I want us to be thinking about uncertainty in broad terms, broader than usual terms, broader than the usual terms we think about in microeconomic classes and where we talk about risk and risk aversion. I want to include potential model misspecification and ambiguity across models. Anyone who's been engaged in building dynamic models of the economy and a variety of reasons knows their models at the end of the day are simplifications, approximations, they miss stuff. How do we use them in sensible ways, acknowledging the fact that there's limits to them? Often there's multiple models on the table. How do we weight them? How do we assess them? And the goals of this are to kind of assess this impact of uncertainty on climate policy outcomes, but also to isolate the forms of uncertainty that really are most consequential for these outcomes. That can put on the table issues about where do we want to learn more in order to inform policy. So uncertain climate economics, I mean, for this audience, you're all familiar with these different possible sources. One is climate sensitivity, the temperature responses to changes in emissions. The other one was there's lots of speculation about so-called environmental tipping points. Potentially, there's some dramatic consequences might be triggered as we cross some temperature anomaly threshold or some other type of threshold. And then finally, damages and adaptation. We're pushing economies into places they haven't really experienced. We have to speculate about the ability of adaptation to various different changes. So I'll be featuring today something which you're all familiar with, the so-called social cost of carbon and uncertainty impacts on it. But indeed, the type of research I want that we're focusing wants to go beyond just the social cost of carbon. But the social cost of carbon, as we know, the carbon emissions today alter the climate. This in turn impacts economic opportunities, social well-being, and the future. And this gives rise to a social adverse cash flow. It's a cash, but that social consequence, the adverse consequences are uncertain. So here, the tools of asset pricing come into play. Financial economists think about pricing cash flows and dividends and the like. How about we use those same type of perspective and bring it over to these type of arenas and try to incorporate uncertainties into the so-called social valuation. Okay? So as I say, asset pricing, it was kind of built on how markets assess investment opportunities. But we can really think about assets in very general terms: financial, physical, human, organizational, but also environmental capital. Each asset is a prospective sequence of net payoffs to some investment. Okay? But again, I want to be using those same type of analytical devices to think about social instead of market valuation, because that's what's relevant for the social cost of carbon. So for me, it's advantageous to think of the social cost of carbon as an asset with adverse social cash flows. Now, the social cost of carbon is commonly referred to in policy discussions, but its meanings, targets, and measurements differ. There are two constructs out there that are conceptually different. They sometimes get confused, and mathematically very similar. Okay? One is the local policy impact. I'm going to look at marginal valuation at a possibly socially inefficient allocation of resources. I'm sitting today, I'm thinking about the future. I don't have confidence that optimal policy is going to be implemented, but I still want to assess what are the consequences of different policies away from the current type of allocation. Right? And a lot of the cost-benefit analyses that are done are this kind of local policy impact. The other one I think of as a kind of a global policy impact. Again, marginal valuation, but it's marginal valuation at the socially efficient allocation of resources. And this is what underlies Pigouvian tax policy on carbon emissions. At the same time you're figuring out the Pigouvian tax, the socially efficient Pigouvian tax, you have to be figuring out what the socially efficient allocation is. But then the social cost of carbon again becomes this asset price based on marginal valuation. So you can represent both analytically as asset prices. A lot of research has been done under the first one. The calculations I'm going to talk about today are actually going to focus on the second one. Now, there's a lot of discussion in measurements of social cost of carbon about a so-called modular approach. The social cost of carbon measurement is in some sense interdisciplinary. We need to bring in inputs from various different sources. This has led to things like National Academy of Sciences committees arguing for the advantageous of these kind of modules. There's a social economic module which we project the future evolution of the economy, including emissions of CO2, so you might have paths of CO2 emissions. There's a climate module that says, well, once you know that the emissions trajectories, then we kind of figure out from climate science what the consequences are. Then there's damages. Economists can go back and assess damages once we change the climate system. And then there's the discounting module, typically using a single discount factor, maybe doing some sensitivity analysis into computing a present value. Now, this modular approach has the advantages that it makes it somewhat easier to bring into different research groups and try to integrate the calculations together. And that's why it's appeal. And it turns out, though, that especially when you want to think about uncertainty, this modularization really starts to break down, and you really have to think about these things much more simultaneously. Right? So I think about the pitfalls in this. So if we just imagine some emission scenario that's specified exogenously, well, if I want to think about the plausibility of that scenario, I have to speculate about what damages it's going to induce. Because the damages it's going to induce is then going to cause some type of, at least endogenous policy response. Maybe suboptimal, but there'll be some type of endogeneity. So it's hard to assess, if you've got uncertainty about damages, that's going to affect how we think about these alternative emission scenarios. We really can't think about these kind of separately. Discounting. So it's common to do discounting at a constant discount rate and just look for external sensitivity. But one of the lessons we get out of asset pricing is that discounting needs to be, in some sense, probabilistic to accommodate uncertainty. If there's uncertainty about the damages to the economy going forward, that affects how you should be discounting the cost, the social cost going into the social cost of carbon. So it's not just some discount rate, it's some whole entire discount process that's going to depend, in principle, on on the possible damages that things might induce. What this leads to is the probabilistic adjustments, and these probabilistic adjustments will depend on macroeconomic uncertainty and how that plays out in the future. In other words, this modular approach really, once you want to put uncertainty front and central, this modular approach really starts to break down because these interactions are just front and central right from the outset. That makes the measurement more challenging to get credibility, but it also, I think, makes it much more reliable and sensible. So what type of uncertainties are relevant? Okay. Sometimes I like the notion, when I think about building models, dynamic models, which I love to do, as a type of quantitative storytelling. And if I have multiple models, I might have multiple stories. Each model, none of the models are meant to be exact replications of reality. They're simplifications, but they help us understand the world through the lens of the model. And different models maybe lead to different forms of understanding. So I like to think about uncertainty in broad terms. And this leads to the following categorization that I and some other decision theorists find to be relevant. The first is risk. So this is what we usually teach in economics classes. We talk about risk aversion, we talk about risk premia and the like. Okay? So I think about risk as a situation in which you know probabilities but not outcomes. So in macroeconomics, there's extensive literature on dynamic stochastic equilibrium models under rational expectations. In those environments, economic agents and policymakers know probabilities, they just don't know outcomes. That's risk. I want to use the label ambiguity is when there's uncertainty across models. Multiple models run the table, and these models give rise to potentially different stories with different implications. So when you think about the statistics discipline, it's about how to, in some sense, cope with ambiguity. How do we weight different models? How do we use historical evidence? How do we use prior information in order to engage in this? The third one is, I think, in many respects, maybe the most important. It's the conceptually most difficult one, and that's misspecification. I write down models. There's uncertainty about the models because each model is an abstraction, not intended to be a complete description of reality. So if the model is just approximation, how do I know how far I can push it and still get reliable answers? Okay? So I think that's tremendously important. We don't teach this very well in econometrics classes, but I think in actual use of models, it's vital and central. Okay. So how do we want to think about navigating uncertainty once we speak in these broader terms? So the aim here is you don't want to throw away models because they're, quote, wrong. All models are almost wrong by definition. But you want to use them in sensible ways. So you still want to use the tools of probability and statistics to limit the type and amounts of uncertainties that are entertained. Okay? I don't want to announce that I know probabilities with full confidence, but I still want to appeal to tools of statistics to get some type of limits or bounds on the nature of those probabilities. To do policy, just like risk aversion, we have to think about risk aversion in models with risk. More generally, there's an aversion that one has to confront, and I'll be talking more about this. We have to confront a type of dislike about probabilities over future events. Implementations, what they amount to is the following, is part of the computational challenges and solutions to models, is you kind of target the components of uncertainty that really are most consequential to decision makers in an adverse way. And you make the idea is to then make this all operational. So there's decision theory. I'm not going to go into the details of this. These are some references, but I'm not going to go into this. And there's a bunch of literature coming from a variety of different sources. And for today's talk, I'm going to not do a deep probe into that literature. But coming out of this is going to be, I take a kind of a robust perspective to things, and it's going to lead to an explicit form of a sensitivity analysis that's going to be advantageous in thinking about how to use models. Okay? So how do we adjust, in adjusting for uncertainty in policy and valuation, the idea is to construct these robust policy rules and a corresponding kind of worst-case type probabilities from outcome of a two-player game. I do dynamic versions of this. In order to operational notions of robustness, we might have some social planner figuring out what the right or most sensible policy is. But then to look across different probabilistic specifications, we invent this other player that goes through and figures out how, if you announce that policy, what are the possible adverse assessments that might come out based on your uncertainties. Okay? So what comes out of this is you're not just solving for decision rules, you're at the same time solving for robust decision rules and these probabilistic adjustments that are of most concern to the decision maker. It turns out that those modified probabilities, those altered probabilities, are the ones that we also want to use to make uncertainty adjustments in valuation. So as I'm solving this kind of fictitious two-player games, I'm also getting out the probabilities that I need to make assessments for valuation. So instead of using my best guess probabilities in valuation, I want to be using the outcomes of calculations of this type. Okay. So I'm going to give you some illustrations. Now, let me just put a caveat for an audience like this. These are going to be highly stylized models. I'm going to abstract from some really important stuff that we recognize is in order to illustrate the impacts of these uncertainty adjustments. We're right now engaged in far more ambitious type calculations than the ones I'll talk about now, but I think these have some pedagogical value to them. So part of what I want to show in these illustrations is there's these calls for immediate climate policy implementation, but there's limits to our understanding. So we want to pose a decision problem in which there will be future information about damage severity. We're uncertain about what the damages will be in the future, but in the future we're going to, once you start damaging the environment, we're going to start figuring stuff out. But that's only after we damage the environment. The value of future empiricism in the near term is limited. There is empirical research that likes to look across countries, across regions, and the like to make speculations about what happens as we warm the world more globally. But I think that type of evidence is really hard to fully extrapolate with confidence. And so we're really, in this realm, we're pushing economies into places they haven't experienced. So this is a case where even though we have a data-rich environment, the data doesn't always speak to the places we need to, that we need to know about for designing policy. So again, I'm going to be using recent developments in dynamic decision theory to kind of guide these calculations. Okay. So I'm not going to get into details of stochastic differential equations and the like. I'm going to give you a couple of slides that have these equations, but we're not going to get into any subtlety here. I just want to give some flavor for the way these calculations work. Imagine there's a state vector. Say I mark out the state vector xt, and it's evolving. I'm writing this in continuous time for convenience. So it's got this kind of so-called local mean. That's the mu sub x. That's kind of where you expect it to go locally. And then there's these shocks that hit, these normally distributed shocks. So think of these dw's as a vector of normally distributed shocks, so-called increments to Brownian motions. And a is the decision process. That's the baseline model. That's maybe our best guess. This is where we start from. But now we want to allow this model to be, quote, misspecified. So the way we're going to do it is we're going to say, well, instead of that Brownian motion, instead of those normal shocks having mean 0, maybe they have some other mean. That mean can be history dependent. It could depend on lots of things in the past. It could depend on, it can feed back on the actions or the like. But we're going to introduce these kind of mean shifts into this. So this is for how we address these so-called small shocks. And so when we're doing this minimization part, guarding against misspecification, we're going to be searching over these H's to see how, what the adverse consequences of those are. Okay, and then we're going to have to impose some type of bound or penalization on that in the nature of that search. Now, how about if we hit this with instead of misspecification, ambiguity over models? So now what I've done is I've written that mu x, this kind of local mean, as a function of unknown parameter theta. Okay? Now we may have some distribution. We may have, based on historical evidence that tells us something about that theta, and maybe we use kind of the, what we know about filtering methods or Bayesian updating or the like, in order to construct some type of distribution, posterior distribution over theta. Now, in dynamic setups, there's always this confusion about, or ambiguity itself about what you mean by priors and posteriors, because today's posterior is tomorrow's prior in a sense, in these recursive setups here. But anyway, QT just summarizes, you can call it prior, posterior, depending on your perspective, what we know today about that parameter. But now we want that to be potentially, we don't have full confidence in that calculation. Yes, we can apply some filtering method, but that requires a lot of special assumptions, and it may not be right. Okay? So now what we're going to do is we're going to allow that distribution over the parameters to be some other distribution. Okay? And so this is a case in which instead of model misspecification, we're going to think about how we're weighting over models indexed by theta as potential prior/posterior misspecification. Okay. Finally, let me just talk briefly that we also have these large shocks, these so-called cases in which there's some abrupt change in the underlying environment. There's some jump probability, and the way in continuous time we model this is we announce some jump intensity. The chance of a jump, then, is approximately equal to the time interval times that intensity. So we have to specify the likelihood of a jump, that's this intensity, but also where we jump to. There's a jump distribution. That's what this dp is. When we want to explore robustness, we need to, which we might misspecify the jump probabilities, we might misspecify the jump distributions, and both of those are of interest to us. Okay. Now, how do we do this? If you allow yourself these kind of changes in probabilities in arbitrary ways, you can get extreme outcomes. Maybe you don't even want to get up in the morning because such bad things could happen. you have to put some type of bounds or constraints to get something interesting here. And here's where we use statistical methods to help us out in various ways, or ideas that come from statistics and applied probability. We use this construct, relative entropy. It's got a fancy name, but basically what it is we take logarithms of density ratios, likelihood ratios, and we compute their kind of local expectations. And so we're using statistical methods to figure out, to bound or limit the types of divergence in probabilities which we consider. This approach is common in applied mathematics and statistics. It allows us to exploit lots of nice properties of likelihood functions and joint probability distributions. And then we use the so-called penalization approach. We put a large penalty parameter. It's going to constrain how much we can search across these different possible probability specifications. So large penalties corresponds to small degrees of aversions to either model misspecification or to ambiguity. So what we get here is a different way to do uncertainty quantification. In the scientific disciplines, there's lots of discussions about uncertainty quantification. For us, uncertainty quantification only makes sense within setups of policy problems or decision problems. Why do we care about the uncertainty? Where is it consequential? Right? We do want to entertain uncertainties from multiple sources that I've talked about, but we're going to pose formal decision problems, and they're going to include penalizations over ambiguity, penalizations over potential model misspecification. Formally, we map this into so-called max-min dynamic decision problems with two outputs. This altered probability that isolates uncertainty components that are most consequential, and a decision rule that performs well across alternative specifications. Right? So I talked before about this aversion to uncertainty. Well, that translates here into how much you want to penalize these searches over alternative probability specifications. And of course, I as a researcher don't want to dictate to policymakers exactly how averse they ought to be. So in general, what we do is we kind of conduct two-parameter sensitivity analyses. We vary these penalty parameters and show the consequences. And I'm going to give you some illustrations. Okay. So how much uncertainty aversion? There's this whole literature in uncertainty aversion, ambiguity aversion, and the like. And the literature, where it's weak is describing methods to quantify or calibrate the ambiguity aversion. We have our own approach to this, and we want to follow the lead of coming out of what comes out of the literature on robust Bayesian statistics. And one of the kind of gurus of this literature from decades ago was Irving Jack Good, and he basically said, well, what's useful is if you're doing these minimax or max-min solutions, when are they reasonable? You ought to be looking at what you're guarding against. You ought to be looking at these least favorable distributions and making sure that they kind of don't look crazy. So as you change the penalty parameters, you can figure out the worst cases, and then you can inspect those. And if they look crazy, then it sounds then you've kind of calibrated things in the wrong way. So we report these implied probability distortions for alternative penalizations and then quantify magnitudes. So again, we think of this social cost of carbon as an asset price. We think about nonlinear impulse responsive emissions to data damages. We need to incorporate these margin utility adjustments. If damages are going to come into play, that's going to affect valuation. We have to do interacting uncertainty between economic damages and climate change. And then finally, we use these uncertainty-adjusted probabilities in order to do valuation. So I'm going to be using a very simplified model here. It's going to be lifted closer out of the macro literature. We've included things like expiration in order to expand reserves. It turns out that component of this model doesn't do a whole lot for us, but we've allowed for it. But it's going to be a simplified model that in absence of climate change, capital is going to produce some type of intermediate good combined with emissions determines economic well-being. There's going to be capital can produce output for expiration, for investment, and for these intermediate goods. Then the climate side comes into play. Well, the emissions also damage impact the climate. The climate damages and alters the economic well-being. So it's going to be kind of highly stylized integrated assessment model. This is just some mathematics of the economy absent any form of climate change. It's just kind of adjustment cost model with long-term stochastic growth opportunities. So here, what I want to do is start putting on the table some results here that we've extracted from the climate science literature. So we need to put input in terms of this mapping between emissions to temperature changes. So there's one way that the climate science literature does these model comparisons is they run these pulse experiments. You give a whole bunch of different climate models pulses, and then you tabulate what those model responses are to those pulses, to, say, emissions pulses. So we're just like impulse response functions that macroeconomists are used to, but you're doing these through these fairly complex climate models. There's no way we can stick a climate model inside our economic model and have something tractable. So we're looking for simplified characterizations. And the climate science literature uses this to make model comparisons. Okay, so what we're looking at here are calculations over 144 different models. And these are models, some of these models focuses on the mapping emissions to carbon in the atmosphere, other ones from carbon in the atmosphere into temperature changes. And so we're just taking these type of calculations out of the kind of climate literature and tabulating the results here. So what you'll see is with this emissions, the pattern is that you, after about 10 years, you get a peak effect, and then things flatten out. Okay? Now, the blue dashed line shows you the kind of mean across all 144 different responses. And I've also given you the 25th and the 75th percentiles. The actual plot itself had the full envelope here, but it's not showing up on my slide, unfortunately. But we can also give you the upper and lower envelope that is, of course, somewhat bigger as well. So this shows you the divergence or the heterogeneity in the climate model predictions. Now, for us, for a macroeconomist, you pull things out 100 years. That's more than that's already extrapolating the how reliable you could hope the macro model is. So, 40 years is already long term for a macroeconomist, and 100 is certainly out there. For a climate scientist, this is like short-term stuff. I mean, they'll push their models out for many centuries, and there'll be further dynamics that show into play. But roughly speaking, things just go flat here after 10 years. But there's considerable heterogeneity. Now, for me to call these probabilities, I have to treat each model ex ante as equally likely. I have to assign the exact same weight to each model in order to get these percentiles into probabilities. And that weighting may seem somewhat arbitrary. And so part of the sensitivity is what happens when we adjust the weights from equal weights to ones that could be slanted. Because the equally weighted specification, maybe it's a nice benchmark, but it's not clear you want to stop there. So what's important for a calculation is kind of those limit points after those flat lines converge, and this just tabulates what those look like. So arguably there's a fair bit of uncertainty here about if you emit carbon in the atmosphere today, what its consequences are going to be longer term. And this histogram captures that. So this is the uncertainty coming from the climate side. So now I'm going to have a somewhat stylized, fictitious model of damages, which has even less in the way of empirical inputs, but I'm going to use this for illustrations. There's lots of discussions about damages and kind of what the damages should be. And there's a lot of heterogeneity in people's calculations. So I've plotted here kind of a typical one of these kind of damage functions, which up to a temperature anomaly of about 1.5 things are very, very modest. Here I've put a threshold. The threshold is at 1.5. After that, things start becoming more severe. How severe they become is where the uncertainty shows up. And so that's captured by this region, by the shaded region here. It could be very, 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 very modest. Some of Nordhaus's calculations have been much more on the modest side of things. Weitzman used to argue for potentially much more severe type potential damages. This is all in situations in which we don't have historical experience, so it involves lots of speculation. And then the intermediate line is some type of average between. Right? So we're going to load in a bunch of different curves here, of which the middle one is kind of the average of those different curves. And again, we don't really know how to weight the curves. We're going to start off equally weighted, and then we're going to look at the consequences of shading things. Now, this is for a temperature anomaly of 1.5. So, it used to be people thought would discuss the temperature threshold of anomaly of 2 as the critical one. Now it's been shifted back to 1.5, depending upon discussions. We're going to also put uncertainty about where this damage threshold gets crossed. It's going to get crossed somewhere between 1.5 and 2, and that's where the big shock comes into play. We're going to treat that as a Poisson event. The Poisson event is going to be triggered as to where this threshold is going to kick in, and beyond this threshold, then the damage functions are going to become much more curved, but in uncertain ways. Okay, so we're going to, formally speaking, there's just going to be one jump. There's going to be, and the jump's going to be captured by this, this curvature in the damage function. So here, in the future, you're going to learn stuff. You cross that threshold, you're all of a sudden going to know a lot more about the damage function, but not today. Okay? That's to illustrate this effect of information coming down, coming into the future. So prior to this jump, there's going to be uniform distribution. After this jump, then you're going to know the curvature. But you still won't know the climate sensitivity. Right? This is just a discussion about instantaneous objectives. So basically what we're going to imagine is some type of the damage functions, or these damages are going to kind of proportionally impact the output and consumption in the underlying economy. And we've rigged the model so that we can solve for an undamaged version of it, and then as a computational trick, and then we can superimpose the damages on top of it. So here's the type of calculations we can get. Remember that red histogram I had before about climate sensitivity? That histogram presumed that all 144 different models were treated as equally likely. That's just kind of a baseline guess. Right? The outcome of our calculations, depending upon the penalization, is to then slant things, to change those probabilities, to say, well, I might be worried that things are more loaded towards the high climate sensitivities. And so for a particular specification of the penalization, you shift the probabilities from this original equally weighted one into what's given by this blue histogram. Right? And if I change this penalization across model ambiguity, I can make that can be very modest, or it can become even more extreme. The more extreme case would then just load everything up on that super high damages. It's an intermediate range we think is most interesting. Now we also have these risk-adjusted probabilities to these damage curvatures. This gamma 3 is kind of a statement of the curvature that occurs in the damage function. We start off with things being equally likely. That's the red histogram, which is flat across all the different damage curvature values. And then for a modest, arguably a modest adjustment in terms of things, we can get the intermediate case. That's for an intermediate level of penalization. Then as we make the penalization even lower, so we tolerate lots of possible misspecifications, one can push yourself more towards the extreme. Again, it's the intermediate point that I think is the most interesting one, but it can range between these different pieces here. Right. Now then associated with those different forms of ambiguity aversion and concern about misspecification are things like the social cost of carbon. Okay, so the social cost of carbon as a baseline, if we kind of just use averages, we just get the red line, and this is in a log scale here. As we go to the lower amount of adjustments, we go from the red line to the orange line, and then the green line, in the more extreme case, all the way to the blue line. If we take the intermediate case here, notice we're increasing the social cost of carbon by 30 to 40% off of this trajectory here. So these type of adjustments we're talking about are non-trivial, and they can be made fully operational. Now, the way things work here is you don't wait until you know the curvature of the damage function. You do act now. You do reduce emissions substantially now. After the damage curvature gets realized, that's information, it could be good news. Oh, damages aren't so bad. It could be, really bad news. Oops, they're, very extreme. We find a very asymmetric response here in terms of the emissions post-realization of the damages. There's a very small range under which you're treated as, which you suddenly become more bold, and then a much bigger range over which you kind of continue caution, or if anything, make things even more cautious. So the kind of curvature of this is of, say, particular interest to us in our analyses. It comes out of this dynamic learning. So let me just summarize what we get out of this example. The solution to our decision problem identifies two key results. The planner exhibits initial caution until damages are more fully revealed. With this information, the decision maker might be more wary or more bullish, depending upon the information. But there's a pronounced asymmetry. There's a small fraction of more bullish responses and a clustering of responses that are more cautious. So here's areas of active research. We've only got we've only got one policy tool in place there, and that's how to reduce emissions. You say, and here you could reduce it through a carbon tax or something. But our current research is simultaneously allowing for reduced emissions, but also investment in R&D that could increase the likelihood of say, technological solutions in the future. This now puts two types of policy aims on the table. Now, there's lots of literature discusses the relative merits of these two different type of approaches, but what this puts on the table is how uncertainty affects them, and uncertainty can potentially affect them in very differential ways. Some of our initial calculations is the R&D subsidies are much more impacted by the uncertainty adjustments than the emissions adjustments. So, kind of a new feature to that, or a new component to the discussion of R&D subsidies comes into play here. And we're also engaged in, I've given you models of the climate side here that's, in some sense, highly linear. I've characterized it by those impulse response functions and the like, but arguably that's missing some potential nonlinearity that might be triggered by the climate in the climate system. And so we're collaborating with climate scientists to look at nonlinear counterparts to these carbon dynamics that could change things in the future and produce more in the way of tipping point-like behavior. So let me just kind of conclude here. Uncertainty matters for policy tools like the social cost of carbon. Understanding the sources of subjective uncertainty in models used by private sector or by governments will make economic policy all the more effective. Finally, let me quote from my favorite American philosopher: "Education is a path from cocky ignorance to miserable uncertainty." Yes, uncertainty can be miserable, but there exist tools that allow you to at least navigate it, confront it, and address it. Thank you very much for your time.
Thank you very much, Professor Hansen, for this inspiring lecture about climate change and uncertainty. We have some time for a few questions from the floor, so please, if you have a question, raise your hand. Well, you have a question. There's a question somewhere down there. Please, can you please get the microphone? I'm sorry, I cannot see the light straight into my eyes, so I cannot see anything.
So I have two questions. One is on a technical level, and the other one is on how to use this in policy making. So on the technical level, I was wondering, in the weighting of the multimodal results, you are still limiting yourself on the domain of the results. So you can shift how they are weighted, so you can shift the histogram of the model results, but you don't leave the domain of the results, right? You can't shift it past the maximum that was in the multimodal results, even though a misspecification could also mean the maximum is too small. So that's the technical one. And the other one is, how do you safeguard against motivated reasoning by people who apply this? So if I have a hidden policy agenda to not have climate action, then I would weight it in one way, and if I have a hidden policy in the other direction, I would weight it the other way.
Okay, so let me address the first one. The first point had to do with, are you entertaining enough when you engage in consideration of model misspecification? So that's always going to be a challenge. As I indicated, model misspecification is in some sense the conceptually most challenging part of this. There's a sense in which we're looking at model misspecifications that are challenging for a statistician to try to figure out. But you might be worried that that ties your hand too much. There might be forms of misspecification that in some sense are out there that have much more dramatic consequences than being statistically subtle. So in order to do any type of tool like this, you have to somehow bound the types of uncertainties which you want to consider. So when we do model misspecification, we're putting a lot more on the table than a so-called robust Bayesian person would put on the table, but in truth, we can't put everything on the table. So we do have to limit ourselves, and in these calculations, we're limiting ourselves in ways that are motivated by statistical discrepancies, but there's other things which someone can do. Now, the other question is about, I think if I interpret it correctly, is couldn't you potentially abuse these methods? That is, what I could do is I could imagine that I'm working out these distorted probabilities, and then the decision maker is going to come and kind of use them and decide what policy that the decision maker wants, and then figure out the way to justify it by choices of things like ambiguity aversion. Well, first of all, ambiguity aversion is going to push you in very special ways, so it's not going to give full latitude to in terms of that type of activity. It's going to be fairly disciplined, and it leads to a theory of caution and not to and the like. But there's nothing that would stop a decision maker from misstating or misrepresenting the types of uncertainties out there in ways that could abuse any type of statistical tools, including this one. I do think there's another problem related to this, and that is how does one communicate this to policymakers, in the sense of the best hope here is you communicate this stuff to the policymaker advisors, and the policymaker advisors can then help educate the policymaker in terms of what's sensible and the like. So, yeah.
David over there.
It was really enlightening and excellent presentation. Two things. If you're a policymaker, you'd like to have this stochastic adaptive decision making dependent on some policy action. And so to some extent, you really need to maybe simplify some element, but to say, God, if you take policy A, is that what happened? That's number one. Number two, you have a global assessment. Can you really develop algorithms that you can break it down to sub-constituents? Because no one really thinks about the world. Everyone thinks about themselves.
That's a good point. I mean, there's lots of illustrations out in the literature of this kind of global versions of climate change and using models of the world economy and single decision makers. And of course, that's a very contrived view of the world policy making. And moreover, it misses the fact that climate change has a very heterogeneous impact. It's going to impact some economies much more than others and the like. And these calculations absolutely are guilty of those type of simplifications. We're very much interested and very much trying to figure out tractable ways to put much more heterogeneity in terms of the exposures, which I think is critical from the standpoint of policymaking. The other part, which we have very little to say about, is when you have multiple policymakers, how do you convince them to interact in productive ways? And that requires much more subtle game theoretic type arguments about policymaking and political economy issues that perhaps this could be input into those discussions, but that's stuff which we haven't engaged in. And then policymakers themselves may have limited horizons, limited times of commitment and the like, and that would also make the policy part of this much more maybe realistic and more complex. So on that part, I think it's a very important problem. On that one, I'm not sure we have anything very new to say relative to what is currently out there in the literature.
Thank you. I think we can stop here. Before we go to lunch, from the city of Rimini, I would like to present Professor Hansen with a small present.
Looks like a gorgeous map, so I thank you for taking the time to listen, so anyway.